We have our brand new notepad out in front of us called The Gas Laws, an introduction really to the behavior of gases in terms of the kinetic molecular theory, in terms of pressure, volume, and temperature, and how they affect the behavior of gases. We know that in nature there are three states of matter. You've recorded those as solids, liquids, and gases. This particular chapter is devoted to just the special behavior of the gas molecules. What makes them unique from the other phases of matter is that they have complete freedom to move around. You know how solids are held in a rigid three-dimensional shape, very little freedom to move around. As a matter of fact, they just really are in fixed positions. Liquids have the ability to flow past each other, but really not to change other than the shape of the container. Their volume is fixed. But gases, holy cow, any container you put them in, they're going to occupy the entire space. Gases, we realize, are mostly empty space inside of their container, that the size of the compound that they actually take in is pretty negligible to the volume of the container. So solids, liquids, and gases are indeed the three phases, our focus of the new chapter, specifically the phase of gas. Since gases move, we understand that they possess kinetic energy. Kinetic energy is the energy of motion. So we've recorded that. We've also studied in our past something called potential energy, the energy of a position. So if I were to hold a book up high, that would be potential energy. And if I release it, of course it's going to fall to the ground. Now that potential energy is converted into kinetic energy. Maybe in a science class somewhere, sometime, you even talked about the formula for kinetic energy being 1/2 mv squared. M is mass, v is velocity, which might be a little unusual for us because a lot of time v stands for volume in this unit. But in this particular case, the v stands for velocity, the speed at which you're moving. So 1/2 the mass times velocity squared. So molecules move. Solids a little bit, we said. Liquids a little bit more. But gases, they would possess the most kinetic energy of any of those three phases of matter. Part of the very final part of this chapter, Graham's Law of Diffusion, I know as we read those vocabulary words we had said Graham's Law, we'll actually be calculating using the mass of molecules, the speed of molecules. We can figure out how much kinetic energy they have. So in order to understand the motion of these molecules, we talk about something called the kinetic molecular theory. And if I just break it down, how do molecules move? That's truly what the theory will discuss. Atoms in all forms, solid, liquid, gas, are in motion, but specifically this theory talks about the behavior of gas molecules. Since all forms are in constant motion, we'll focus on the gases. And to do so, we make some three basic assumptions. In other words, these are three things that we say are true, but they're not really true. But they make the math friendly. Three basic assumptions that are close enough to be true to hold the math instead of high-level calculus, basic algebra. The first of those assumptions talks about the size of the molecule. If I were to consider the container that a gas molecule would be in, and I have a blue molecule and it's zipping around, and I have let's say a little black molecule zipping around, and I have all kinds of these gases inside the container, and freeze frame, just stop it from moving. The size of the actual molecules in the container is so darn small, we say it's zero, that the size of the molecule is negligible. Now what will that do? You see all these gas laws that have V's involved in them, volumes? We're not taking the time to subtract out the size of the individual gas molecules from the size of their container because it wouldn't significantly change the value. Since atoms are so darn small, let's just call them zero. Now is that really true? Do atoms truly occupy space? Yeah, sure they do. Does a flea weigh something compared to a big German shepherd? Yeah, sure it does, but does it significantly change the weight? Not at all. So we're saying in basic assumption 1, atoms have no space. Not true, but good enough for this particular set of formulas. Basic assumption 1 says the atoms occupy a space of zero volume. There's a second basic assumption that you wrote about in your notes. It says that particles of a gas move rapidly in constant random motion. they're going to travel in straight lines until they ricochet and change direction, very similar to like a pool ball. It's going to travel in a straight line until it either hits another ball or the side of the pool table. Thinking about that really sets up that vocabulary word known as the random walk. So if I were to have, let's just say, a container, and I place gas molecules in there, I'll put some blue molecules, I'll put some different molecules in, and I start tracking the path that those are following. All this random walk is saying that I'm going to travel in a straight line. Oop, I hit the side of a container. That's what pressure is, hitting a container side. Then I'm going to change direction. Oop, now I hit this guy, so I'm going to change direction and so forth. That those random walk, or the individual path that a molecule travels, is independent of anybody else in that same container. Now, is that necessarily true? Probably not. Sometimes we have molecules that are attracted to each other or repelled to each other based on electrostatic charge. So sometimes, hey, this blue and this red, they might have oppositely charged regions. We know opposites attract, so they're going to cluster. Well, that would change the path of the walkway. Or if they have like charges and they came near each other, they would repel, and that would change the pathway. So we're saying they ignore each other. 99% of the time that's true. Molecules of gases ignore each other and they travel in straight lines. So we call that a random walk, the constant random motion of a gas particle. And then we talked about the third basic assumption of our kinetic theory. We said that all collisions are perfectly elastic. What does that mean? If two objects collide, bam, and they ricochet off, anytime you have two objects collide, there's a little bit of friction there, isn't there? And friction is actually a transfer of energy giving off just a tiny bit of heat. But see all these temperature, these T variables in the gas law? I don't want to subtract out the tiny amount of friction heat and then have to accommodate the T, the temperature. It would be impossible to measure how much heat was lost when a molecule collides. So we're saying we're going to not count that. We're going to say all collisions have no net loss of energy. Not really true, but we're going to say it's true. So collisions are perfectly elastic simply means the total energy remains the same. Those three basic assumptions turn a pretty complicated math equation involving high-level calculus to very easy, straightforward algebraic expressions. The three basic assumptions are mostly true. We're going to hold them to be true for the kinetic molecular theory. So thinking about the motion of molecules and the random walk that they travel, we had a little story in the text you were reading about a bottle of perfume. My mother in church. You place her in a pew and let the perfume start to diffuse. According to the kinetic molecular theory, if, and that's a big if there were nothing in the way, that molecule of perfume, or in this case, so perfume here, it would actually reach Mexico City about 90 minutes later. I mean, that's traveling pretty darn fast. Wouldn't it be nice to get to Mexico in about 90 minutes? I could do that. You could go on a weekend, be back. But it doesn't happen, does it? So why? Why don't they ever make it there? And you all talked about, I see in your notes, there's a lot of stuff between here and Mexico City that's going to change the pathway of those perfume molecules. So anytime there's a collision, I know that it's going to change direction. So it never quite reaches Mexico City due to all the things that you've listed in your notes. Buildings, other air molecules, any other object it might encounter is going to change its direction, change the random walk that it will follow. So as we go on and define that term random walk, I even drew a little picture of it just moments ago, that aimless path that molecules travel as they diffuse from high to low concentration. You know what that diffusion term, most kids will say, hey, I remember hearing that in biology class, right? Or osmosis is another term you remember saying in biology class. It's the same idea. When I opened that bottle of ammonia, it was diffusion bringing it to your nostrils, that from high to low concentration until we have that equilibrium reached. Gas molecules move in that random constant motion until we have an equilibrium established. Constant concentration from one area to the other. We measure pressure of a gas in 3 different units. Leave it to us in chemistry land to have 3 ways to measure pressure. We have the metric system, we have the English system, and then we have something that is more commonly used here in our lab is a millimeter mercury. We have gas pressure units measuring all of the billions and billions upon billions, and might I add the word billions, of collisions anytime it's striking another object. Do you know right now you're experiencing air pressure? Why don't we feel it? Why don't we feel the billions and billions of air molecules colliding against us right now? You know what we have pushing out with an equal force is pressure. When do you notice air pressure? It's almost like when it experiences a change. You ever gone up high in altitude and have your ears pop? If you're driving up in a mountain area, or if you're had the experience of going up in an airplane and your ears have popped, the air is thinner up there, and so all of a sudden there's a pressure change, and that membrane in your ear is going to pop to let the pressures equalize. Or have you ever kind of gone down deep in the swimming pool, like if you dive into the deep end and have your ears pop, you go down deep and the pressure is greater against your body and your ears pop to, again, equalize the pressure. So we don't really notice air pressure now because it's equal on the inside and outside, but boy, you notice it if it gets different on either side. So the term gas pressure really just measuring how many collisions against the side of the container. Billions and billions and billions of molecules hitting create a pressure. So mathematically, of course, pressure is equal to force per unit area. If I increase the force of a collision, I've increased pressure. If I change the size of the container, I'm affecting pressure. So really I think of pressure equal collisions. What can I do to affect the number of collisions, and I'll affect the pressure? Well, what's the opposite of having molecules with great pressure? You start taking molecules out and you get something known as a vacuum. That seems to be a term students are familiar with, just saying a vacuum is the absence of particles. So the opposite of pressure is a vacuum, the absence of particles. If there's nothing in there to collide, there would be no pressure, and we refer to that as a vacuum. So empty space caused by simply removing the number of particles in your container is known as the vacuum. When we think about atmospheric pressure being measured by a barometer, we start up to the idea of what standard units are. With an atmospheric pressure, it's the air molecules hitting the object. We have a barometer in our lab. Maybe you've noticed it. It sits under the fume hood. It's really just a ruler stick that bends around and measures how much mercury, just like a thermometer climbs up and down with temperature, mostly down this winter, might I add. Pressure does the same thing. So if I just consider what barometers do, let's suppose, and draw this with me so we understand what pressure is and how a barometer works. Add this onto your notes. This is a big old tub, let's say it's of mercury, Hg. So I've got a beaker filled with mercury. And I'm going to place an inverted long test tube in there. So this is my inverted test tube. We're drawing this. I place a meter stick, just kind of graduations as I go up. And the meter stick could be inches if you live in America. Generally, you're looking at a metric system, so it's a millimeter measuring this meter stick. Air pressure is the push down on the surface of this beaker, holding the liquid mercury. If air pressure is pushing down, what happens is you start to see the mercury climb up inside of the inverted test tube. So you can see the more and more and more pressure I have in terms of atmospheric pressure, the increased push down on the surface of the liquid mercury, the capillary action of that liquid mercury is going to shoot that column of mercury up high. This is a high pressure day. If, like today, we have a low pressure day with, snow and icy rain coming in, the weather is low, we have fewer molecules pushing down on the surface and the pressure would drop. So air pressure is really measured by how the push down on the surface of a if it's not mercury, most aren't anymore. It's a liquid alcohol. But idea is just whip out a ruler stick and measure how high is the mercury column, and we're getting a reading on the mercury of the day. And those units that we use actually are in 3 different units. The millimeter mercury is the ruler stick that we just talked about. It's the unit that will be delivered to us when we read our barometer in the lab. In a laboratory setting, it's the most common unit. Pascal is the metric system unit. The standard international unit of pressure is the Pascal. Because it's so small, we're more likely to hear that with a kilopascal, a kPa. We know that 101.3 is the standard pressure reading on a kilopascal. So I'm standing at sea level. It's a 0-degree day, not high in a mountain where the air is thin or deep down in a valley where it's a little bit greater pressure, but right at sea level, I whip out a ruler stick at 0 degrees, it'd be exactly 760 millimeters high, the standard pressure unit in a millimeter mercury. And of course we have our American version, the atmosphere. The 1 ATM stands for an atmosphere of pressure. We need to be very familiar with those 3 values. Do you see them on the far poster up here, the brand new knowledge poster? I've recorded those for us to help us begin the memorization. Just as I promised in our thermochemistry chapter, eventually you'll remember 4.184 is water. I said to memorize it, but don't worry about it because you'll just remember it. The same thing will happen to you with those pressures. You'll just remember them eventually. We have to have the ability to convert from one pressure unit to another. 101.3 kPas is equivalent to saying 760 mmHgs, which is equivalent to saying 1 ATM. 3 different ways to measure pressure depending upon the unit. And really converting between them is as easy as setting up a conversion factor, want over given. Our standard pressure units, again, equivalency is provided for us on this slide. 1 atmosphere, the same as 760 millimeters mercury, the same as 101.3 kilopascal. The temperatures in our new unit must always, always, always be in a Kelvin unit. So we have to be comfortable in converting from our typical Celsius into the Kelvin temperature as well. If you haven't yet, it's really a good idea. Record that conversion. We're going to take the Celsius temperature that our thermometers come in the laboratory setting and simply add 273 Kelvin units to get to the Kelvin temperature. Now, it's an important reason why we need Kelvin. It's known also as the absolute temperature scale. Whoops, I spelled that wrong already. Absolute. Simply because there are no negatives and there are no zeros in a Kelvin temperature. And if that is really important as I start to look at my gas laws, notice how temperatures on the bottom in Charles' law, temperatures in the bottom unit here, it makes no sense. I can't have a 0 down there, and I can't have negative energy. There's no negative heat energy. So I can't have a negative scale. If I had negative temperatures, I would come out with negative volumes or negative pressure, and that's nonsensical. So we always convert to the Kelvin temperature to avoid those algebra issues, taking our Celsius and adding 273. We have a few practices we can look at in terms of going from one unit to the other. In our first example, we're asked to simply convert 1.5 atmospheres into a kilopascal, and also into an mmHg, the millimeter mercury. This is probably now the top of your next page looking at example 1. So our given 1.5 ATMs, and I'm just going to simply think about what I want over given using those standard conversion values. I'm asked to change to a kPa, that's the unit I want, over the unit I'm given, which is an atmosphere. Notice when I pull out those standard values, ATMs simply cancel and I'll have converted. So just right from the previous slide, I'm looking at those standard values that equalize those pressures. I know that 101.3 is exactly the same thing as saying 1 ATM. They're equivalent values. Atmospheres cancel and we have converted. So I'm sure you've probably hit. Let me catch up. 1.5 times 101.3, and we have 151.95 kPas, which abbreviates for a kilopascal. Let's do the same. Start with the atmosphere, but this time we're going to convert into a millimeter mercury, which I commonly call just mmHg, which again is what our laboratory barometer will read. I know that 760 millimeter mercury is equivalent to 1 atm, so that's an easy enough conversion, 1.5 times 760, and here we're looking at 1140 mmHgs. Now friends, I have a side note that's not in your text, but it's part of any other standard chemistry course. I'm going to add a word that you'll often hear in place of millimeter mercury. It's called torr. It's a person's name, is why I capitalized it. Torr is a unit used to represent pressure. It's the same thing as saying millimeter mercury, but sometimes, and most often except in our book, it's called torr, T-O-R-R. All right. I think there's one more practice, but what I'll ask is that I'll stop the recording here and ask that I'll just come around and take a quick peek and see if we get a common answer. I'm pretty confident how far we made it today actually is a perfect spot to ask you to just practice with the section worksheet 10.1. Got a great idea on kinetic molecular theory. We introduced the concept of pressure, talked about the Kelvin temperature, all great foundations to start tomorrow. A little bit of the gas laws, Charles, Boyle's, and Gay-Lussac. A little bit of algebra tomorrow. Alrighty, so I'll stop her there.